Well, now we're going to prove the Cauchy-Euler theorem. And all that really means is that we are going to show how this equation is essentially equivalent to this one. And so we're going to start with this one. And I already mentioned the substitution that we're going to use. Actually, maybe I'll make this part of the proof. We're going to use this substitution. X equals e to the t. So of course, t equals ln x. And that means that dt dx, take the derivative of both sides with respect to x, we would get dt dx equals the derivative of this with respect to x, which is just 1 over x. So we're going to use those three. Well, this is the only substitution. This is what you get when you solve this for t. And this is what you get when you differentiate both sides with respect to x. Okay, so one thing we have in this equation is a dy dx. And I've started this already. dy dx is just dy dt times dt dx. But dt dx is 1 over x. So since we're done here, I'm going to rewrite this. That's going to be 1 over x dt dx times dy dt. I'll use that for a substitution later. And now we've got d squared y is dx squared. So I broke that up into two things. This is the derivative with respect to x of dy dx. And I'm going to go a little bit to the right before I start moving downward. This is the derivative with respect to x of dy dx, which is this. So instead of dy dx, I'm going to write 1 over x times dy dt. And then from here, I'm going to have to write a little bit smaller. Let's see, 1 over x times, I'm going to differentiate this using the product rule, this function times that one, with respect to x. So I'm going to get 1 over x, the first, times the derivative with respect to x of the second, plus the second times the derivative of the first. Well, the derivative of the first is negative 1 over x squared dy dt. So all we did is product rule. All right, well, this is equal to, the first term is 1 over x times d, in parentheses, I'm going to put d dt, dt dx. You can see that's just d dx right here, times dy dt. So all I did is substitute d dx as d dt times dt dx. So those are kind of canceled to give you the d dx minus the second term, 1 over x squared dy dt. I've got 2 more lines to get in, but I don't think I'm going to be able to fit them all down there, but I'll put 1 more line down there. This is equal to 1 over x times d dt, 1 over x, in parentheses. All I'm doing is the substitution we did right here. Over there, dt dx is 1 over x times dy dt, and then minus exactly what we have here, 1 over x squared dy dt. And I need 1 more line, so I'm going to have to move up to here. And I'll rewrite what we've got. I'm going to write d squared y over dx squared. D squared y dx squared is equal to, I'm going to factor out, notice we have 1 over x, so that's 1 over x squared. There's a 1 over x squared there as well, so we factor it out and we get 1 over x squared times, in parentheses, d squared y over dt squared minus dy dt. So I'm going to use this again, and I'm going to use that again. All right, I'm running out of room. I'm going to start right here. F of, well, x is equal to e to the t. So I'm going to put f of e to the t equals f of x, and then I'm going to write what we know f of x to be, which is, well, here's f of x. So f of x is all of this. It's equal to ax squared d squared y dx squared plus bx dy dx plus cy. 1, 2, I hope I can fit it all in here. We'll make it happen. All right, well, this is, and I'm going to move down to here just to make sure I have enough room, equals ax squared then in parentheses, let's see, here's d squared y dx squared, this, so I'm going to, which is this. So I'm going to have 1 over x squared times in parentheses d squared y dx squared minus dy dt, closed parentheses. And I can close the bracket, actually. That's just ax squared d squared y dx squared, which we replaced with that. All right, I'm going to continue to the right. Plus bx. And bx is multiplied by dy dx. And dy dx we have right here. So 1 over x dy dt. Sorry, I'm writing a little smaller now. That's 1 over x dy dt, and then we just have plus cy. Okay, wow, I need 2 more lines. Well, let's see what happens here. Equals a, let's see, ax squared. Oh, the x squared goes away because we've got x squared times 1 over x squared. So this is d squared y dt squared just kind of multiplying this through minus a dy dt. So the x's went away, and I've got a times this second derivative minus a times this derivative. Now we're moving on to the b's. Plus the x's cancel out, so I get b dy dt, and we'll just keep plus cy the same. And that gives us equals, let me say implies that f of e to the t, which is where we started, it's equal to this, but we're going to simplify a little bit. Notice that these are like terms, and then notice if I factor it out, I'm going to get a b minus a times dy dt. And I think that gets us where we need to go. That's exactly where we needed to be. Hopefully you can see that. But it's exactly this, which is where we needed to be. So that was a lot of calculus and chain rules and product rules, but a pretty straightforward substitution, which got us from this to this. So when we get an equation that looks like this form, all we got to do is convert it to this simpler to deal with equation, second order, ordinary differential equation, linear, with constant coefficients.